Recording started. Okay, let me share my screen. Okay, so okay, you guys will be able to share my screen, I'm sure. Okay, fine. So today's concept is about memory allocation. Okay, so this is a bit long. Okay, the class will definitely be a bit long. Okay, please be patient. If you want break in between, let's take the break. No problem. Okay, and this is the notes I prepared. Okay, this is the notes I prepared. I'll share you this as well. It's not part of the PPT. The PPT has some normal documentation, but these notes I prepared with my own words. Okay, so I will share you this as well. Okay, no issues. But here there will be many new words, new keywords coming in. Okay, so don't get panic, so you will get used to those keywords. Okay, so this document, right, this document every time it looks new to me because there are those kind of concepts. Okay, this memory allocation and all, but this is the most advanced concept in Spark. Okay, so the moment you submit your job to the Spark, what happens, how memory is allocated, all this kind of stuff is given here. Okay, so do not worry. So let's go through this one by one. Okay, so once you after this class, right, after this class I'll try to explain you as simple as possible, but after this class just go through this document again. Okay, why I want is, even you understand, do not understand, no problem, but there are many keywords here involved. So even I forgot those things, because in real time we will never bother about these things. But it's just how memory allocation happened in the background. Okay, so how you can that if you know how it's happening, then how you can optimize it. You can do optimizations on top of that, right? So that's why after this class, this memory allocation concept, right? You can just go through it again. Okay, go through it again so that you will understand, you because you just listen the new words, right, new terminologies. So that's why after this class, if you go through this again, then it will be good for you. Okay, so let's start. Okay, so memory allocation, that's the concept today. Okay, what is memory allocation? Okay, so we discuss about executor executor and driver. If you remember correctly, I'm talking about master slave architecture. Let's go to HDFS. In HDFS, it is name node and data node. Okay, name node is the master node, data node is the data node, slave node. Okay, now let's come to resource manager. In sorry, let's come to yarn. In yarn, resource manager is the master, node manager is the slave. Okay, in Spark, driver is the master, executors are the slaves. So far clear, right? So we know this thing. So master slave architecture, all these three concepts are following the master slave concept, right? So here we have master as well as the slave. Okay. So who is the master here? Driver is the master, and slaves are the executors. Fine. But so to run this driver and executor, okay, driver and executor, you need to give some memory to it, right? Some memory, assign some memory to it. Okay. So using Spark submit. Okay. So this is a Spark submit command. Okay. Spark submit command. So we are supposed to discuss this, right, yesterday, day before yesterday. So I will just brief it here, just small thing. So then we can in tomorrow's class we will discuss on how Spark submit and all happens. Okay, the moment you submit your Spark application, right? So how you are going to submit your Spark application is, so this is the rule. This is the thumb rule. You can just remember this thing. Okay, you can just remember, because the moment you say Spark submit, because in production, right, you need to submit your Spark job to the application. Okay, you need to submit your Spark application to the cluster. Okay, so how you are going to connect to that cluster? Okay, that via this location. So in production you will get to know where this master in the sense that resource manager, we can say, right? In yarn, resource manager is the master, right? So that master, so if you specify this address, it will connect, it will help you This Spark submit will help you to connect with the master. Okay, and the deploy mode. What is the deploy mode here? Client. I told you three modes. If you remember, if you go back to the previous class, I told you three modes. One is one is client mode, one is cluster mode, one is local mode. Okay, what is client mode? If you remember client mode, the moment you submit the Spark application, the driver will run in the client. The client means my system. In the my system only. If I submit my job from the Spark application to the Spark cluster, the driver will run in my computer. Okay. If we go with the cluster mode, the driver will run in the cluster. Driver will run in the cluster. Okay, so that's we know. Like if you go to the previous class, we discussed this. What are the deployment modes? There are three deployment modes: client, cluster, and local mode. Local mode means the cluster is in your system, the driver is in your system. Okay, in your laptop. Okay, both. Now executor memory. Yesterday we discussed about this problem, right? What is the executor memory? So I told you that this is the executor. These many executor nodes. This is the memory of my executor. These are my CPU cores. Now we spoke about that executor. If you remember, what is this? Yeah. So we discussed this problem right yesterday. You guys aware of this problem? Okay. So let's take 20 executor memory mission. Okay, 20 executor missions and 5 CPU core thing, and each for each executor node, and 6 GB of RAM. 6 GB of RAM. Okay, so this is what we discussed. 6 GB of RAM in each executor node. Okay, the moment you say is 6 GB of RAM, how? This is the main concept now. Now this is the main concept. We will deep dive into this concept. The moment I asked for 6 GB RAM in the executor node, what happens in the background? Simple. The moment you ask for, let's say, the moment you ask for 10 GB of executor memory, 10 GB of executor memory, what happens in the background? What happens in the background? Does all this 10 GB, the amount you requested, will directly ascend to the executor, or is there something that happens in the background? Okay, so some memory out of this 8 GB, whatever the memory you asked for, right? Out of this memory, only 60% will go to the executor memory, and that 40% will be used for the user memory. So that happens in the background. But how everything happens in the background, let's discuss. Okay, now, so before we if we come to Spark submit again, okay. So here I specify the executor memory. So you guys can ask me how you're going to mention the size of the executor. So here I'm specifying the executor memory as 4 GB. In this case, in previous example, it's 6 GB. Then I will go with 6 GB here. Okay. If driver memory is 2 GB, I'm just going with 2 GB here. That's it. So you can specify this memory here. So, but for now, you can just remember these three things. Okay. The moment you say Spark submit, and the master in the sense that resource manager who is supposed to accept your location. So you need to say, right, to see when you write a letter, you need to address that person, right? You need to write that person's location as well. Okay, when you post that letter into the post box, so you need to mention that address of that receiver, right? That's why we are giving the address of our receiver. Okay, that master will receive this command. Okay, and deploy mode is client. You know, right? If it's deploy mode client, that means the driver program will go and sit in the my laptop or cluster. Let me know. I know in the morning you will be definitely lazy, but yeah, just be involved here. Okay? We are putting efforts to make things fair, right? So the deploy mode means where will driver go and sit? Is it in the cluster or in the local machine from where you submitted the application? Come on, Eda, Anusha, Karthik.
Cluster.
I told you deployment mode, right?
Yes, sir. Yes.
So if I client means where will my driver program go and sit? Is it in the my laptop or in the cluster?
Cluster.
Cluster.
You say cluster. Okay. So what are the other two modes we have?
Client. And local.
Yeah, local.
Local.
Local. So we have three deployment modes:
Hmm.
client,
Cluster.
Cluster.
cluster,
And
Local.
then local.
Local.
local. Okay. So what happens in client? Where will this?
Deploy,
Hmm?
deploy, I mean,
Deploy mode. Okay. So where deploy mode means like your application will get deployed into the Spark cluster, and the driver program will be sit in which location? Either whether it's in your executor in the sense, I mean this laptop or cluster. Who is client here? The moment the person who submits a Spark application, right? See, the client to a company is the person who gave the task, who gave the work to that company, right? Client means in the real world, client means the person who gave work to that company will be called as a client. Okay, so who is the client here? Who submitted this Spark application? Okay, so from which computer laptop this Spark application is submitted? Fine. So I told you client, cluster, and local. Let's leave local for now. Client and cluster. What does cluster and client? Here itself you have the answer. Client and cluster. Okay. So client means the driver memory will go and sit in your laptop from where you submitted this Spark command. Okay, client mode means. Cluster mode means
So this it will connect to the resource manager, right, sir, in client mode
exactly resource
from the
manager.
local thing.
Yes, resource manager.
Yes, sir.
This,
This
this is the
for the
this is the
cluster
resource.
it will be for the master, sir, application master.
Sorry, cluster
It
is
will
for.
not be in the machine. It's not
Hmm,
in the machine.
hmm.
It will be in the master node.
Okay, this is master node. Driver program.
Yes, yes,
Okay,
sir.
okay. So that will be in the master node, but in the real time, right? Like I mean, in that one specific example we discussed, right? That will be in the master node. That's right. But what happens is in production, right? You'll have many applications coming in. Okay, so many applications coming in, and this Spark, right? This Yarn, right? Yarn will not launch all the applications. I mean, all applications because it will have let's say 10 applications. Okay, 10 Spark applications submitted by the 10 different users. Okay, for these 10 separate applications, you need to launch driver, right? Definitely, because driver is the starting point. Application master, inside that you will have a driver, so it needs to launch the driver. Okay, so if you launch all 10 drivers in the master, the resource manager, right, we discussed, so then it will hit the memory issue. Okay, so in the production what happens is how many let's say two at least out of 10, right? Maybe two it will launch in its resource manager master node, but the rest eight, right, it might go and launch in the node managers. I mean, node managers, right? Resource manager, it might launch only one or two or zero as well, and the rest, right? It will go and launch in the node managers. So, but that's all in the real time. But yeah, what you said is like it will be launched in the this resource manager only. But here the question is difference between client and cluster. So the client means I submit this job from this laptop. That means the driver program will spin up in my laptop. Okay, client. Okay, but cluster means the moment I submitted it, this driver program go and sit in the resource manager or the node manager. It depends. It depends. It's not in my hands. It's in Spark's hand. Okay, but when someone says client mode, that means that driver program is going to run on your laptop. So what happens is if the driver program runs in your laptop, if something happens to that driver program, that means there could be multiple issues. Some you accidentally closed it. Okay, if somehow the job is running and you accidentally closed it, then you lost your application, you lost your results. Okay, if some network issue happens, some OS failure happens, if something happens, you will lose those results, right? If you launch it in your laptop, but if you launch that in the cluster, then then you can if you switch off your laptop, if you disconnect it for some time and connect it back, still you will have your application running on the cluster, right? So that's why in the real time, in the production environment, you will go with the client mode only. Sorry, you go with the cluster mode only, not the client mode. Client mode is for our testing purpose, we can say. Maybe in some cases you will say, do client mode, but rare cases, but mostly we'll go with the cluster mode only. just go through this definition again. Client versus cluster. Okay, local mode means is nothing. It's just for testing purpose. If you started learning Spark, right, you might use that local mode. That's it. But client and cluster important. Client means driver program will get started in your laptop. Okay, but in real time, right, it's a cluster mode. That means the driver will go and sit in the cluster. That's it. Cluster. Why I'm saying cluster is because it will be sit in the resource manager, node manager. Both are part of cluster, right? So that's why we go with the cluster. Okay. So that's what happens. And the moment you ask for executor memory, the memory allocation will get started. Okay. So how this memory allocation happens, we will see. The driver memory is for 2 GB. Driver memory is also, I'll let you know how this happens. But these two other requests I gave, right? So this is the master. I mean, for this Spark execution, right? Executor memory and driver memory. Both are very, very important, right? So let's see how executor memory and driver memory are allocated. Okay, nothing but a mission. Okay, so just think in memory means nothing but a mission, and mission needs a memory to work, right? That's it. So mission needs some memory, some RAM, right, so to work on. That's it. Let's see. When you submit a Spark application in a yarn cluster, the moment you submit the Spark application in an yarn cluster, then yarn RM will allocate an application master. The yarn resource manager will allocate an application master. Okay, we know, right? Application master we just discussed, and start the JVM driver in the container. Fine. So by this I understood that it's a like the moment yarn you submit a Spark application in the yarn cluster, yarn resource manager means that yarn's a master, right? That master will allocate an application master and start the JVM driver in it. What is JVM? You know, right? JVM means Java Virtual Machine. That means whenever you run Java, right? If you guys work with Java, you might have better idea on this. But JVM means Java Virtual Machine. That means and you run a Java application. This JVM is kind of a container, okay? Container to when you run the Java program, the system needs to understand that Java program, right? So that it will go through some process. Okay, it will be converted into bytecode, and that bytecode is get executed. Some stuff. Okay, just think JVM means some internal execution. That's it. Some internal execution. That's it. Okay, to run your Spark application. The moment I say select in Python, right? Python, you will say that let's say the list dot append of one. How things happen in the background, you know, that list appending, you're appending with one, that's it. But how things happen in the background, so that will where it will happen in this JVM only. Okay, the moment you say list dot append of one, so that all those kind of process and all will happen. But JVM is a big lengthy concept. Okay, so the whenever you have time or something, just go and check for this JVM, what is Java Virtual Machine. That's it. Okay, now the driver will start because the driver will start in the application master with some memory allocation which you requested. Okay. So let's see. Here I requested 2 GB of memory. That means my driver supposed to start with 2 GB of memory, right? I requested for 2 GB of driver memory. That means my driver program will start inside an application master. Okay. Now my driver memory should be 2 GB. How much? 2 GB only, right? Come on, you can be interactive here. So you can unmute yourself.
Yes. 2 GB.
Yes, sir.
2 GB. 2 GB means it's supposed to be 2 GB. So let's go with simple. I want 1 GB. I'll keep it simple. Okay. So let's go with one by one. So the driver memory will start with some memory allocation which you requested. Let's say I request for 1 GB of memory. Okay, 1 GB of memory. What happens is to get physical memory for a driver container, okay, we need to use two configurations. Just remember these two configurations, okay? Just whenever someone asks, you can remember this configurations, okay? Spark dot driver dot memory is one configuration, and Spark dot driver dot memory overhead. What is memory overhead? Right, we'll see. You will see everything. Okay. What is Spark driver memory, JVM memory, and Spark.driver.memory means memory overhead. So non-JVM memory. That means with this, I will say that my execution will happen inside this JVM memory. Okay, I told you right. In Python or Java or wherever you go, so if you go and write that some line of code, okay, that code will be executed inside a JVM. So outside JVM, it cannot be executed. Okay, so in this here, we can see two memories here. One is JVM memory and one is non-JVM memory. So what is JVM memory? Spark driver memory. What is non-JVM memory? Spark.driver.memory overhead. Fine, fine. Okay, let's see. Let's assume if you ask for Spark driver memory of 1 GB, 1 GB, as for 1 GB. See, why this? Let's say the moment I submit, I'll ask for, here I will ask for 1 GB of memory. Okay, 1 GB of memory. Let's say I ask for 1 GB of memory. Fine. Now, the moment if you ask for 1 GB of memory, you will get 1.384 MB. 1.384 MB. Why? Why? Why we will get that 18384 MB? Let's see. Let's see. Because as per only 1 GB of driver memory, you getting right. So I'm asking for 1 GB of driver memory here. Let's forget about this executor memory for now. Driver memory. So I'm asking for driver memory. The moment yarn resource manager starts the Spark application, I mean starts application master and launch a driver memory driver program there, then I'm specifying that this driver's memory should be 1 GB. But here what I got 1.384 MB. Why I got that 1.384 MB? Let's see. Let's see. The default value of Spark driver memory, because before that you see here, right, to get a physical memory of driver container, okay, we need to use two configurations. One is Spark driver memory, one is Spark driver Spark.driver.memory overhead, non-JVM memory, both JVM and non-JVM memories combined. You will get the final physical memory. Okay, so combined, if you ask for 1 GB, you're going to get 1.384 MB. Where does this extra 0.384 MB came from? Okay, so that's what this Spark memory overhead came into the picture. Okay, so the default value of this Spark driver memory is maximum of 10% of your requested memory and 384 memory. 384 memory is hard coded. It should be minimum 384 MB. That means what happens is, okay, so maximum of 10% of requested memory. What is 10% of requested memory? What is the requested memory here? 1 GB. That means here it will be 10% of 1 GB is equal to 100 MB, right? 100 MB, 384 MB. Okay. Now, what is the max of both out of these two values? Max is equal to 384 MB. Right? This is the max. Someone join. Okay. So by any chance you got disconnected, just let me know once you join back. Okay. So you understand this thing? The default value. This is the rule. This is the formula. Just remember this formula. The formula you remember. Okay. The moment I say driver memory, there are two things: JVM memory, non-JVM memory. JVM memory is the place everything execution, all these things will take care. Non-JVM means it's just for maintenance. Okay, maintenance. Just think for now. Just assume it's for maintenance. Okay. Now, the moment I ask for 1 GB of memory, 1 GB of memory, 1 GB of driver memory, let's say, I will get 1.384 GB. 1.384 GB. Why? Why I will cut that is, this extra, where does this 0.384 MB came from? Where does the extra 0.384 MB came from? That came from my driver memory overhead. Okay. So is this value going to be constant? No matter how much amount of driver memory you need, whether this 384 MB is going to be constant? No. Why?
Yeah.
Because, yeah, someone want to say something? No? Fine. Why? Because this is the formula. The default value of Spark driver memory overhead is equal to maximum 10% of the requested, maximum of two values. Maximum of two values. The one value is 10% of requested memory, comma 384 MB. Okay, so the 10% of 1 GB is 384 MB. Sorry, 10% of 1 GB is 100 MB, comma 384 MB. That means max of these two numbers is 384 MB. Let's go with here I request for 1 GB. Now let's go with 10 GB. What if I request for 10 GB? Can anyone let me know how much amount of memory I will get? I need here for Spark memory overhead. Okay, just let me know. See, I'm taking 10 GB now. Okay, so 10 GB. Now this is the formula. 10% of 10 GB means how much? 1 GB. Right? Now, out of this 1 GB and 384 MB, which is the max?
1
1,
GB.
1 GB. That means I will get, if I ask for 10 GB driver memory, I will get how much memory now? How much memory? 10 GB plus this 1
1
GB of memory overhead. Right? Memory overhead. That means
Yeah.
11 GB. Clear so far?
Yes.
Okay.
Yes, sir.
Anusha, you clear?
Yes, sir.
Okay. Please be involved. So if you do not understand this concept, let's ask me here itself. Then I will again reiterate on this concept. You clear, right? How this memory
Yes,
overhead is
yes,
being
yes.
calculated. This is the formula. Just
Yes,
remember
sir.
this. A plus B whole square is equal to A square plus B square plus 2AB. You remember that formula. Similarly, the moment you ask for driver memory, remember this formula. That's it. Whenever I ask for 1 GB of memory, Spark will give me 1.384 MB. 1.1 GB, 1.384 GB, 1.3 GB, let's say. Okay, why this extra 0.3 GB coming from? Because this is where the Spark memory overhead came into the picture. Okay, now if I ask for 10 GB, it says 1 GB. I mean, extra memory overhead is 1 GB. That means you will get 11 GB. Now I want you to answer this next question. Okay, so here I will give let's say 20 GB. Well, let me know how much. What will be my final? What will be my final memory overhead here?
Uh, 2 GB.
2 GB.
Two.
Okay. So 2. Here, if we go here, it will be 2. That means
2
if we
GB.
ask for 100 GB of memory, sorry, 20 GB, right? We go on with 20 GB. Yeah.
Hmm.
How much amount I will get here
Yes.
finally?
22 GB.
20. 22.
22 GB. Perfect. 22. Okay. 22 GB. 2 GB plus 20 GB. Right? 22 GB. Simple, right? Simple. Driver memory is very simple. Like the moment you ask for some amount of memory, you will have two things here. One is JVM memory, non-JVM memory. Non-JVM memory will be calculated via this formula. Maximum of 10% of your the requested value, comma 384 MB. Only I think let's see. Let me tell you. If you ask for maximum of so I think 384 MB means 3 GB. Maybe if you ask till 3 MB, this formula applicable. After that, it will be 10% of your overhead. If you ask for 3 GB, it will be 300 MB. Okay. So till 3 GB, it will be under 384 MB. Okay. So let's say till 3 GB. Okay. Till here, it will be 384 MB only. But if I go with 4 GB, what happens? It will be above 300, 384 MB. Okay. 400. Okay. You can remember this. Okay, so till 300 3 GB you will get 384 MB, but beyond that you are going to get the 10% of your maximum cluster. Simple, right? Simple. If someone says my driver memory is 3 GB, then you can definitely go and say that 384 MB. That's it. If someone says my driver memory is 4 GB, then you will say your memory overhead will be 10% of 4 GB. That is 400 MB. Simple. Okay. So after 3 GB, it's greater than 384 MB. That means 10% of your okay. Fine. Now, as we all know that Yarn will allocate 1 GB of memory for driver JVM and maximum this request this driver memory overhead as well for container. Okay. But what's the purpose of this 384 MB? What's the purpose? As for 1 GB, as for 1 GB, but why are you giving 1.384 MB? What's the purpose? What's the purpose for that extra 0.384 MB? Okay, this overhead memory, this overhead memory is used by the container process or any other non-JVM process within the container. Within the container. Okay. So what is this overhead memory used for? It is used for container process or any other non-JVM process within the container. I'm again repeating. This is used for container process, or non-JVM process within that container. Okay. So what is that container process? It could be OS related things, right? Yeah. It could be OS related things. It could be Spark related things. Okay. It's never involved for this 384 MB, never involved in Spark's execution. Spark execution. A driver needs to do some execution, run some steps, but those steps will never be run in this 384 MB. This 384 MB means, I told you, right, the moment you request for 512 GB of laptop, you'll get very less amount compared to that 512 GB. So you'll get only, I think, 484 GB or something. That extra 16 plus 12, 28 GB will go and you get used for your system applications. Okay. Similarly, here, if I ask for 1 GB of memory, it is allocating my extra memory overhead, so that that extra memory overhead will be used for my system related task. Okay. Container related task, non JVM task. Okay. JVM is execution. Whenever someone says JVM, it's for execution. Non JVM means non execution. Okay. What is the non execution task and all? So that will be taken care by in this memory overhead. Okay. Super clear, right? Okay. Note, just note, this Spark driver will never use anything from memory overhead. It uses only JVM heap memory. Okay, that means this memory overhead, right? Spark never going to use it. That means I can clearly say that this 1 GB memory is used for Spark, and this 384 memory is used for that container. We can say container. I can say laptop. I can say mission. I can say that executor, whatever you call it as. So this extra 3.84 MB is used for system applications, system related task, non JVM task. Okay, non JVM task. Fine. System related task. Just remember that. Okay. Now let's see one more example. For example, if you ask for 4 GB Spark memory, then you will get 4 GB Java heap memory and 400 MB of JVM overhead memory. Overhead memory, because we just not discussed. If it's 4 GB, you will get 400 MB here, right? So same 400 MB. Okay. Once allocated, it becomes your physical memory limit of your Spark driver. See, that's what it happens, right? Once allocated, once this memory is allocated, it will become the limit, physical memory limit to my driver. Okay. Now you have three limits here. Three limits here. One is Spark driver JVM cannot use more than 4 GB. Okay. Driver JVM cannot use more than 4 GB. Non JVM cannot use more than 400 MB. 400 MB. And your total size of memory cluster, that driver is 4.4 GB. Okay. Your container cannot use more than 4.4 GB of memory in total. Fine. Fine. What happens? What happens if I these memory limits are violated? So this is the rule. Okay, this is the rule I said, but somehow this rule got broke. Rule got broke because rules are meant to be broken. That's what some people will say, right? So, but somehow it got broke. Then you will see out of memory exceptions. Out of memory. What happens? Out of memory exception. Okay, out of memory exception. What is out of memory exception? Means that you trying to do something. Let's say this Google Drive, right? So where is my Google Drive? So there will be Google Drive. So that Google Drive is out of memory currently, my Google Drive, right? If I try to upload some file into my Google Drive, will it take it? It will throw me that out of memory exception. How it will say is, Google will never say that you have out of memory exception. No, Google will say that you are running out of storage. That's it. Oh yes, out of storage. Okay. That's what it says. So now in this here you will face this out of memory exception. Okay. Okay. Fine. Fine. Now the driver is started with 1 GB of JVM heap, and the driver will again see. Now I asked for 1 GB of memory, driver memory. The driver is started with 1 GB of JVM heap. Heap means I will let you know. I will let you know this on heap, off heap. Okay, just ignore the heap. Whenever I say heap, just look for that execution. JVM execution. Let's consider that for now. But I will let you know what is heap versus, because I have this definitions here. Okay, nothing but on heap memory means on heap in memory in Spark refers to the memory allocated with the JVM Spark executor. Okay, and this is the primary memory space where Spark stores and process most of its data, most of data and objects during execution. Okay, so this is what on heap memory. This is what off heap memory. Off heap memory is used for JVM, but located inside the JVM's managed heap, which reduces garbage collection overhead. So you'll get to know these things, but it's a bit complex for you know. But I'm not going to dive deep into that. These are the definition. I can explain you more on this definition, but just no concentrate on these things. Okay. Okay. Now where we are. So now the driver will again request the executor containers, right? The driver will again. So the driver is allocated. Driver is fine with its memory. I request for 1 GB of memory. It got 1.384 MB. Fine. Fine. Now the driver will request for the executor containers. Executor containers from the now the driver will again request for the executor containers. Okay, from the yarn and yarn RM. Yarn RM means yarn resource manager. Resource manager. Mhm. Manager will allocate a bunch of executor containers. Okay, the driver will again see. I'm repeating again. Once driver memory is fine, driver is the master, right? Once master is fine, master is well set, master is functioned, and master is ready to run. Okay, then it will try to launch its slaves. Okay, once the master is in, it will try to launch its slaves as well. Okay, now how many executors it needs to launch, how many what is the memory of that executors it needs to launch will be decided now. Okay, will be decided. Now let's see how many executors. Let's forget about the executors. Let's discuss about single executor. Okay, single executor. Now let me go here and bring this here. You see, I have this config of this Spark executor is equal to 2. We'll take this here. So far clear, right? In case of any doubts, just let me know right now. I can just reiterate on this. Let's go with single executor. That's it. Driver memory is fine, right? You are clear with the driver memory. Any doubts so far on driver memory?
No.
No. Driver memory, you're clear. Good. Now, once driver is done. What is the next thing we need to launch? Just half an hour more. Just be concentrate, be focused. That's it. If this half an hour, next half an hour you're focused, then you will get most of the concepts. Okay, it will be that easy, but you need to remember the names. That's it. Okay, what happens once driver is done? What is the next thing we are going to launch? Executor, right? Executor, right? I told you, right? Master slave. What is the master slave here? Master, once master is launched and the slave will be launched. So if you go with Hadoop, it will be name node and data node. If you go with yarn, it's resource manager and node manager. If you go with Spark execution and all, you will see this driver memory and executor, driver and executor. Okay, driver is the master here. Where driver will get launched inside an application master. Okay, the moment a driver is launched with the memory we asked for, right? If there is an issue, it won't launch, but it got launched. Lucky, we are lucky that driver is started now. Once driver is started, it will try to launch executors. Okay, it will try to launch executors. Now, with on what is the configuration of executor? I gave here that my executor configuration, some configuration with that configuration, and this Spark executor cores. So how many cores I'm giving here? I'm giving only one. See, this is the actual thing. This executor cores means CP cores. Okay, so always you see executor cores, that means CP cores. Okay, CP cores. Executor instances. Okay, executor instances. That means how many executor instances? Let's say for time being one. I need one driver, one executor. Okay, so here I'm going with. You can ask me, why can't I go with driver instances? No, driver doesn't have any instances. Okay, driver is only one. Okay, you can never go and launch an extra driver. Okay, driver is only one. There will be only one leader. Okay, now executor driver, once driver is launched and good, driver is good, then it will try to launch executor. So how many number of executors it needs to launch? It will be decided by this configuration called spark dot executor dot instances, and it's one. In each one spark executor you can remove. This is for cp cores, you can say cp cores I'm requesting. Okay, for one executor I'm requesting for two cp cores. 2 to 5 is the optimal value, right? 2 to 5. So between 2 to 5 I will try to go with one value. Okay, now let's forget for this. Okay, executor memory is some 1 GB, let's say 1 GB. Okay, and spark dot executor instances is equal to 1. That means one executor is supposed to get launched. Okay, one executor is supposed to launch. Let's see how this will get launched. And do you think this 1 GB is directly get used utilized by this executor? Let's see that as well. Okay, where are we? Okay, now driver is started. Okay, now driver is started with 1 GB of JVM key. Now, the driver will again request for the executor containers from the yarn, and yarn resources will allocate a bunch of executor containers. But in our case, it's only one executor. Okay, but how much memory do you get for each executor container? How much memory? I request for how much amount of memory? 1 GB of executor memory. But how much memory I will get? Let's see. Okay, now again to calculate that we have some formula. The total memory allocated to the executor container is the sum of this formula. Overhead memory. Again you have overhead memory here. Again you have JVM heap memory here, off heap memory here, PySpark memory here. But in case of here, there is only two things: JVM memory and memory overhead. That's it. Spark.driver.memory and spark.driver.memory overhead. That's it. Only two configurations here. But here we have four configurations. Four configurations. See, there are four configurations to calculate your exact executor memory. Okay, it will be overhead memory. You already know overhead memory in driver. You already know that will be overhead memory. That's it. JVM heap memory means your normal memory, driver dot memory, right? We saw here. Where is this? Yeah, this is JVM memory. JVM heap memory, you can say. Okay, heap memory. Okay, JVM heap memory. Now let's go here. Here is this JVM heap memory and off heap memory, PySpark memory. Okay, what are these two things? What are these two things? Okay, let's ignore for now. Let's not ignore for now. Let's say that there's some new concepts to us. Off heap memory, PySpark memory. Okay, let's put them aside. These are the two important things. Why I'm talking about these two important things is these are very important. Is let's see. Spark driver. See, does anyone getting disconnected and joining back?
Um, it happens, or sometimes we all get logged out and log in.
Okay,
Yes, sir.
fine.
Once we try to join the session again, it will show us that it is ended up.
Okay. Fine. By any chance you got disconnected or something, directly call me. Okay, because this is important concept. I hope this is we are going good. So far you have any doubts? Driver got launched, right? Driver got launched with the memory we asked for. Okay, but it got some additional memory. Why? Because of this memory overhead. Fine, clear. Once driver is done, the next thing is executor.
Execution.
Driver will try to trigger this executor launches. It will try to launch these executors, right? How this memory allocated to the executor, that's what we are going to discuss now. Okay, so this is the formula for this executor container. Okay, executor container is overhead memory, one thing, JVM heap memory, off heap memory, PySpark memory. Okay, let's see what are these things. These two are not important. These two are can be 0, okay, but this overhead memory cannot be 0, okay. This error memory is what we requested for. Okay. Now, Spark driver will check all these four configurations to calculate executor memory requirement, and then ask yarn resource manager, okay, for executor container memory, because application master is supposed to go to this resource manager and ask that I need these many executors with this much amount of memory, this much amount of containers. Okay, let's see. Total executor memory is equal to Spark dot executor memory overhead. Let me make bad, very bad. Mm,
Sir,
yeah.
Karthik said he's not able to speak in this app. The mic is off, not able to on that mic. Please tell sir. It's then
O-
disconnected automatically.
Okay. Ping you or in the group.
He's there in the group.
Mm, okay. Um, Karthik, you're unable to speak in the class. Okay. I'm not sure what to do. I couldn't see anything here. Can't even. I can't even do anything here. Maybe. Okay. For now, if you have anything, at least try to put it in the chat. Okay. I hope you are able to hear us. Okay. Just if anything needed or anything required, any doubts or something, just put it in the chat. That's it. Okay. We can discuss there. Okay. Now let's continue with our right. Perfect. Cool. Okay. So this is a formula. Okay. Remember this formula. Okay. Remember this is formula. A plus B whole square equal to A square plus B square plus this. That's it. So this is the formula. The moment you ask for Spark executor memory, this is the executor memory you will ask for. Okay. This is the executor memory you will ask for. Let's put it first. You will get this additional memories as well. Additional memories as well. Okay. The default value for third and fourth configurations are not defined. Not defined. That means you can consider them as zero. Them as zero. Right? These two, right? These two are default values are zero. Okay. Default values are zero. Default value 0 is equal to 0. So see, so far class is clear, right? Or you feel any boring, nothing. So just let me know. So far, I hope this class is clear. I'm because if you see, I'm still here at the executor only, starting of executor only, because I can just complete just like that. But you guys won't get that. Okay, that's why I'm going much repeating the names and all again and again. Okay, so that you will get used to those names. Okay, so these two, okay, these two are default values are 0. Okay, so you do not need to bother about these two things. These will come into the picture in the most advanced places. Okay, but for now, for your level, this is ignorable. Okay, even I never use this off size and this PySpark memory. Okay, I mean, I do not need to do that, because nowadays all these memory allocations and all is automatically taken care. Okay, do not need to worry about that. Okay, but if you work in typical production systems, clusters and all, so you might think. But as a data engineer, most of the times you're going to develop the application, then it's auto managed. There are many tools. Let's say Glue, KWS Glue. It's auto managed everything. Okay, so you do not need to worry about all these things. Okay, now let's continue. Yarn cannot allocate 8 GB container on a 6 GB machine, right? Why I'm saying this is because because it says that there is not enough physical memory before we ask for driver or executor memory. We should check with cluster admin for the maximum allowed value. So why I bet this kept this point here is, let's say the moment I launch my cluster, here I'm not specifying any instances type. That means I need this type of laptop, this type of, let's say when you're going to order your laptop, you specify that I need this type of laptop. Okay, in real time. Okay, but in the Spark related thing, right? So you will use missions, some node instances, we can call it as instances. Instances means node types, we can call it as node. Node type means let's say in Spark, right, there are different teams. Okay, one team might need different nodes. That means they need 2 GB RAM and 10 GB ROM. Okay, they need those type of instances. But there could be one more team that need 10 GB RAM, 10 GB RAM, 100 GB ROM. They need those type of instances. So what happens in the real time is in the production is, so they will provide all types of types for you, all types of nodes for you. What happens is with those types you can select. They will give you the option which node you want, which type of node you want. I want you then you'll go and select, I need a node with 2 GB of RAM. Okay, you cannot select those values. They are predefined values. You cannot change those values. Okay, you'll go with, let's say you want 100 GB of RAM and 1 TB of ROM. That cannot happen in the real time, because real time you won't get that configuration. If you want, you can go and request, and they will give a such node for you. Okay, but you can request that type of it. So um, what happens is, so if you select this instance type, okay, then that memory is limited for you. That means in that instance, you will have, let's say, 8 GB of memory. Let's say in my system, in my laptop is 6 GB RAM and 512 GB ROM. So imagine, can I request can Karthik come and ask me, sir, in your laptop can I run 8 GB 8 GB memory, 8 GB RAM? Can I go and use your 8 GB RAM? No, it's not possible. Why it's not possible is, my laptop's maximum value is 6 GB RAM, but you're asking for 8 GB RAM. No, it's not possible. Similarly, the moment resource manager, right, it has some limit, physical limits. Okay, let's say that physical limit of that nodes are, let's say nodes are 8 GB. Okay, 8 GB. Now, the physical limit is 6 GB, but you're asking for 8 GB. Okay, that means you have extra 2 GB. You're asking for extra 2 GB. So will it give it that? No. Why will it give? Because you're asking for extra 2 GB, which it doesn't have. Extra 2 GB doesn't have. That's why the before requesting for the size, just check with your admin. If you're in a production type of environment, just check with your admin. Okay, admin, or check for some default allowed values and all. Okay, some default value. There will be some place where you can look for these default values. Just look at that. Okay, then only you can request for these things. Okay. Now, I hope we are recording, right? Yeah, we are recording. Okay, fine. Now it cannot happen. Now, if you use yarn rm, we should look for two configurations. Yarn rm resource manager, you look for two. Okay, one is one is yarn dot scheduler dot maximum hyphen allocation hyphen mb, and yarn dot node manager dot resource dot memory hyphen mb. Okay, let's see. I mean, two configurations. Just remember these things. These two, just remember. For example, let's assume you are using AWS C4 large instance. So this is what I spoke just now. C4 large instance. That means this type of setup for your EMR. EMR, I will let you know. Elastic Map Reduce, EMR means, okay. AWS EMR means you wanted to. Till now I spoke about a cluster, but how this cluster is started. This is EMR. Okay, I'll show you how a cluster spin up in EMR. Okay, just you will go there and you will specify all the details you need. Then you will launch that cluster. Okay, so I will tell you how this EMR is spin up. Okay, so the moment you spin up your EMR, you specify your instance types. Okay, here I'm going with C4 large instance. Okay, that means it says that C4 large instance comes with 3.75 GB of RAM. Okay, 3.75 GB of RAM. That means, can I go and request for 8 GB here? No. Can I go and request for 4 GB? No, because it's only 3 GB, 3.75 GB of RAM, right? That's the limit for that instance. So that's why you can never go beyond this. So that's why it's good to be aware of these values. Okay. So you launched EMR cluster using C4 large instances. C4 large instances means this 3.75 GB RAM. The TMR cluster will start with the default value of yarn scheduler maximum allocation MB. That is 11792 MB. Okay, that means you cannot ask for a container for higher than 1.792 GB. That's your physical memory limit for each container. Even if you ask, you are not going to get it. See, it launched with 3.75 GB of RAM. Okay, if you launch for 3.7 GB of RAM, it's going to restrict it. That means 1.7 GB. That means out of this 3.75 GB RAM, which you got when you request for instance type, you got this 3.75 GB of RAM. Now what happens is the yarn scheduler maximum allocation MB is set to 1.7 GB. That means this yarn scheduler maximum allocation MB. If you clear LabZ, it says that maximum allocation cannot be more than 1.7 GB. That's it. Simple. Okay, 1.7 GB maximum allocation. That's it. If anyone asks beyond that 1.792 GB, that means 1.793 GB. That's it. It fails. It fails that you are requesting for more than that. That's allowed. Okay, this is not allowed. 1.793 GB is not allowed. That's what it says. Even though you request, you're not going to get it. Okay. Now let's assume you ask for Spark executor memory of 8 GB. So you'll get 8 GB for the Spark executor memory, and you will get 8 memory of overhead. Okay, so that's the total physical container of physical memory of your container. Okay, now that means you have three things here. So executor JVM cannot use more than 8 GB of memory, and non-JVM process cannot use more than 800 MB. And again, you can container total physical limit is 8.8 GB of memory. Okay, now how we have I got these values? Anyone know this? How I got this 8.8 GB? How this I request for only 8 GB, 8 GB. Okay, if I ask for it first, initially it will fail because it's 6 GB container. But somehow I request for 8 GB, but I got 8.8 GB. How? Anyone know this? How this 0.8 GB coming from? Extra 0.8 GB. It should be 8 GB plus 0.8 GB, right? Where is this extra 0.8 GB coming from? Okay, where is this extra 0.8 GB coming from? So the moment I ask for driver 1 GB of memory, I'm going to get 1.384 MB. Okay. Similarly, here if I ask for 8 GB, I'm getting 8.8 GB, 8.8 GB allocated to me. Why? Where is this extra 0.8 800 MB is coming from? Come on, I want some answer. You know the answer. Come on, you can unmute yourself. See,
10% of 8
10%
GB.
of 10% of 8 GB. So what is this 10% of 8 GB? What's that memory is called?
Overhead.
Memory overhead.
Yeah,
Exactly,
memory
exactly.
overhead.
Memory overhead. So the 10% of this 8 GB is will be 0.8 GB. So that's what memory overhead. If you remember clearly, here I am discussing about this string, right? Spark executor memory plus Spark executor memory overhead. Okay. So total memory will be Spark executor memory plus that's where I got these values. Okay. Spark executor memory is what? 8. 8 GB. I requested for requested value. Okay, and Spark memory overhead will be 10% of requested value. Okay, 10% of that requested value. What is the 10% of requested value here? 800 MB. Okay, that's why you got that. Okay, and other two is 0 by default 0. That means your formula becomes that your memory requested is equal to 8 GB plus 0.8 GB 0.8 GB plus 0 plus 0. Now in total it will become 8.8 GB. You will get when requested for 8 GB. Okay, cool. Now you're cool, right? Good. So your executor JVM cannot use more than 8 GB of memory. Your JVM process cannot use more than non-JVM process cannot use more than 800 MB. We already discussed, right? Above also we discussed same points. Now you will see out of memory exceptions when any of these limits are crossed. Okay, crossed. That's it. Simple. Till here, I hope you're fine. Right? If you're fine till here, then we will proceed with the next things. Okay. Fine, right? You guys till here fine, right? Or any questions? Anything so far? Any challenges? You need break for 5 minutes? Let's take that. No problem. Do you need that?
No, sir. Continue.
No,
Continue.
sir.
Okay, so you good, right? You good. I
Yes,
know
yes.
these are new concepts, and we are trying to uh, understand that. Okay. Now till here, I hope now driver is started, executor is also started. Fine, everything is in seamless now, so we have no issues so far. That's it. Fine. You will see memory out of memory exceptions if and only if these limits are crossed. This 800 MB, this 8.8 GB, you have limits, and if this is crossed, then you will face these issues. Okay, fine. Now let's dive further. Okay. Now, what is the physical memory limit at the worker node? The physical memory limit of workers should look at yarn dot. If someone asks you this question, okay, what is the physical memory limit at the worker node? That means it's supposed to look at this yarn dot scheduler dot maximum allocation MB for maximum limit. Okay, we cannot get more than this allocation. We just discussed it. So uh, the moment you go and ask for 2 GB RAM, okay, it will first check for this allocation MB. If that allocation MB is the limit you ask for and the limit that it has, okay, it will compare both the values, and if it's allowed, then only it will give you that the amount of RAM it requests for. Otherwise, it won't. That's what we call as a physical memory limit at the worker node. So what is this? That means it's by default, because you saw here, right? If I launch the 3.7 GB of instance, that means you can allocate only 1.7 MB. If anyone request comes and request 1793 MB, it will fail. It will fail that it's not allowed. It will say that it's not allowed. Okay. Now, what is PySpark executor memory? This is what we are discussing now. PySpark executor memory. Okay. So sorry, PySpark executor memory. That thing we will come back later. But now let's go PySpark executor memory. You do not need to worry about PySpark memory. Okay. Spark application is in Java or Scala, but if it's in PySpark, then PySpark memory is critical. To start with PySpark is a to start with. PySpark is not a JVM. Okay, JVM process. It's a non-JVM process. For example, 8 GB requested memory, you are not getting anything from this 8 GB, right? All you have is 1800 MB of overhead memory, and some 300 memory or 400 memory of this 800 memory is constantly consumed by container process and other internal process. This could be system related task and all. Okay. Now your Spark will get approximately 400 MB. So now you have one more limit, because if Spark consumes more than what we accommodated can be accommodated in the overhead, you will see an out of memory issue, right? So if you look from the YARN's perspective, this Spark container memory location will look like this. So heap memory, okay, heap memory. Overhead memory means OS memory. You can think, if someone says other than JVM, anything just consider as an OS memory for now. At your experience now. So your zero experience in data is very. If someone tell you that overhead memory, non JVM memory, anything, just consider that as an OS memory. That's it. Okay. Now let's see, if a container has got more memory, some memory 10 GB, then this total memory is divided into two parts: heap memory and overhead memory. Okay, heap memory, overhead memory. Okay, the heap memory goes to your JVM. Okay, we will call it as driver or executor memory. And when you're running a driver, or executor in this container, okay, it depends on the driver and executor which one you're running. If it's a driver mission, you will call it as driver memory. If it's an executor mission, you will call it as a executor memory. That's it, simple. So point to be noted is memory overhead is a bunch of things. Okay, what is that bunch of things? In fact, overhead is also used for network buffers. So we will be using this overhead memory as your shuffle exchange and reading partition from remote storage. This point I'm pretty sure you won't understand now. But shuffle exchange means we talked about the data shuffling, right? Data shuffling, reading partition data from remote storages and all this kind of stuff. That see, my data is never in my local. Okay, it's supposed to be somewhere, right? So from there I need to get my data. So that means my data need to travel or not? It needs to travel, right? It needs to travel through the network. Then only it can come and sit in my cluster, right? So for that network buffers, we can say network travel, we can say. Okay. Now both the memory partitions are critical for your Spark application, and more than often, lack of enough memory overhead will cost you out of memory exception. Okay. So it says that, okay, this most of the times you will read data into your Spark cluster from remote storages. Definitely, very rare cases, not even rare cases, very rare cases, okay, very rare cases, you will see, you will have data in your local, but most of the cases you need to get it from the remote storages. Okay, now that's why this out of memory overhead, sorry, this out of memory you will face, because if you have this memory overhead and everything is not well set, that you will definitely face out of memory issues. Okay, now you started your application using spark.executor as memory as 8 GB, and executor cores equal to 4. You got 8 GB memory and 4 CP cores. Fine. Now, as you will also get default 10% overhead memory, in total you are going to get 8.8 GB. 8.8 GB. Okay. Now, let's see, out of this 8.8 GB, how much, where these things go, where what happens with this 8.8 GB memory. So if you see till here, executor is launched, fine. This physical memory, I hope you would be fine. Okay, physical memory allocation number. But these concepts right here, even I do not want to deep dive into here, because I know there are few things introduced here. I'm pretty sure we haven't covered those things and all. It's pretty advanced. Okay, so for now, till the executor is launched, fine, you are good, and just know the physical limit. Physical limit, like the maximum limit you can request your AND resource, right? You need to go and request your resource manager. Resource manager, I need this much amount of RAM, but to request that memory, but just look for your limit. What is the allowed values for you? Let's say your allowed value is 1 GB, you cannot request more than 1 GB, right? Just look for your allowed values. That's it. Simple. So the rest of things just ignore. No issues, no problem. This network buffering and everything, just ignore, no problem. If you do not understand, no issues, fine, cool. Okay. These are a bit advanced. So maybe in future, after 1 year into data engineering, then if you come back to these concepts, you will understand better. Okay. Because this is that advanced. Hmm. Okay, let's say I asked for 8 GB of memory. I got 8.8 GB of total memory, right? Fine, 8.8 GB of total memory, fine, cool. Now what happens with this 8.8 GB of memory? Internally, this 8.8 GB of memory is divided into three parts. Okay, this 8.8 GB is JVM memory. JVM memory means execution will happen. That's what we discussed, right? There are two things here: JVM memory, non-JVM memory. Okay, non-JVM memory we discussed many things. JVM memory we discussed many, but let's forget everything now. Let's go into JVM memory. Let's zoom into JVM memory now. Now, in JVM memory, you have three things. JVM memory, out of the memory you got, that 300 MB will go to the reserved memory, okay, and Spark memory pool and user memory pool. What are these Spark memory pool and user memory pool? You never heard of this thing, right? But let's see what happens. Okay, so if you go and see here, this JVM heap memory, right? JVM heap memory is this total, okay, 8.8 GB of memory. Now, out of this, reserved memory is 300 MB, usually by Spark engine itself. Spark, right? Spark supposed to process your data. So Spark needs to have some libraries installed, something installed, some memory. Okay, this 300 memory is reserved for that Spark engine. Okay, and the 60%, right? 60%, right? 60% is where your executor. I mean, I told you, right? RAM inside RAM. Yeah, I told you, right? Hardly if you go and request for 1 GB of RAM, you will get only 60% of that. That's why I told you that 60%. You'll get only 600 MB. If you follow my previous classes, you will understand this. So if I request for 1 GB of 1 GB, eventually what I will get is only 600. Sorry, 60%. 60% is 600 MB. That means if I look for 1 GB of RAM for execution, no, I won't get entire 1 GB for execution. I will get only 60% of it in bulk. Okay, I'm saying, okay. The moment there are many things that's happening inside, but yeah, if someone tells you, ask you for 1 GB of RAM, that means he is not going to utilize all this 1 GB of RAM. Okay, only out of that 1 GB of RAM, only some 60%, that means 600 MB you're going to use. Okay, Spark memory pool, operations and everything start, execution, I'm told you, caching, persisting, everything will happen inside this 60% only. 60%. This what is it for this 40%? 40% is for user memory pool. As a user, you wanted to save some values. This right, what happens with this 60%, right? What happens? I will let you know. What happens is this reserved memory, Spark engine will run. 60%, right? It will take the data, process the data, save the results. That's it. Again, it got removed from the 60% memory. Okay, but there are few things that it needs to remember. user details. Let's say who is running that application, because it needs to write those details back, right? So those locations, user related information, let's say for now user related information. Okay, non data frame operations, RDD operations. So we told you about RDDs, right? RDDs will come and execute it here, but RDDs is the low level API in Spark. Data frames are high level APIs in the Spark, and this Spark, who developed this Spark, is recommending us to go with data frame APIs. So what is data frame? What is RDDs? You'll get to know. But for now, remember that data frame is nothing but a table. RDDs is like just plain text. Okay, plain text. Okay, let's say this is a text, right? So you see everything is a text here. This is a text. RDD is nothing but a text. I mean, just think for as a text now. But this data frame, right? You will see in a beautiful way. It's kind of a table. On a file, you read this file and build a table on top of that. How you build the table on top of that? Via this data frame only, data frame API only. Okay, so this 40% will go for that user memory pool, non-data frame operations, RDD operations. Okay, now let's deep dive in this. Okay, Spark, if you ask for 8 GB executor memory and using Spark executor at memory configuration and got same for the JVM heap, okay, then this 8 GB is divided into three parts. Okay, Spark will reserve this 300 MB for itself. 8 GB. Okay, this that's fixed, and Spark engine itself uses it. That is fixed. They're not going to change it. Okay, now just for simplicity, I'll go with 8 GB here. Okay, for simplicity, just for simplicity, for calculations, right? If I go with 8.8 GB, you might for simplicity, let's go with 8 GB. 8. Okay, 8 value. Okay, now out of those 8 GB, 7700 MB is left. Why? Because this 300 MB is reserved for reserved memory. See, so far clear? Any issues? Anusha, Veda, Ratik. Any issues so far? Or are you following the class very well?
No, sir.
Okay, no issues. Fine, you're
No,
good.
sir.
Good. So you're able to understand, right, concepts?
Yes, yes, sir.
Okay, cool. Anything, just let me know. Okay. So far clear, right? So far clear, I hope. Because you have three things here. Reserved memory, 60% memory, 40% memory. Okay, reserved memory, this 60% and 40%. Out of this memory, 8 GB, this 300 MB will go here. Okay, 300 MB will go here. That's what fixed. Okay, that's why I'm going with some 8 GB. Why I'm going with 8 is just for simple calculations. That's it. Simple calculations. If I go with 8.5 GB, that means 300 is fixed. That means 8.5 GB is left. So just going with simple values. That's it. So let's say you have this total 8 GB allocated. Okay, after this Spark memory override and everything, so 8 GB is allocated. Now 300 MB is reserved. 300 MB is reserved for Spark engine to use. Okay. Now amount of memory you will get for executor memory pool, Spark executor memory pool, is dependent on the this value, spark.memory.fraction.configuration value. So this value is 60% for now. By default it's 60%. By default it's 60%. See, by default it's 60%. It cannot be changed. Okay, and you will get 4620 MB. Why I'm getting 4620 MB? How? Now let's go here. Because of 8000 MB from RAM, let's know for now 8000 MB, 8 GB only. Okay, from RAM, actually it's not 8000 MB even, it will be 1024 into 8. That means 8000 plus 8 into 24. That means 160 plus 32, 192. That 8192 something. But for simplicity, I'm going with 8000 MB. That's it. Now, if I remove 300 MB from here, it will be 7700 MB. Where this 300 MB went? This went to reserved memory, right? 300 memory is gone for Spark engine reserved memory, and we left with 7700 MB. And this 4620 is equal to 60% of 7700 MB. That means 60% of this MB. That's what we discussed, right? So out of this 8 GB, 60% will go here into this Spark memory executor pool, right? So that's where it came here. And this is user memory pool. This is Spark memory pool. This is user memory pool. Okay. So your 60% is in your Spark memory pool, and 40% will go into your user memory pool. What is 40% of 7700 MB? That will be 3080 MB. Okay, 3080 MB. Now, if you combine both this 3080 and this 4620 and 300 MB, it will be 8 GB again. You'll get the final value. Okay, that's how these calculations happen. That's how this 40% happen. Okay, now if you want, you can change the 60-40 ratio. See, you can change the 60-40 ratio. Now let's try to understand these three memory pools. These three memory pools. Okay, but just remember this. I told you about 60-40 configuration, but by default it's 60-40. But if you want to change it, you will change it. But what are the scenarios you are going to change it? What is the situation and everything you need to know for to change these values? For now, just leave it as it. Just remember that 60-40% is the default values. Maybe if you want to change it, you can change it. Okay, but in future, let's see. If you get a chance, I'll let you know. Now, let's try to understand these three memory pools: reserved memory, reserved pool, Spark executor pool, and Spark memory pool and user memory pool. Okay, the reserved pool is gone for Spark engine itself. You cannot use it. That's it. It's gone. Spark engine will run inside that. That's it. Simple. Ignore that. Now, Spark memory pool is our main execution memory pool. Okay, Spark memory pool is our main execution pool because I told you, right? If you ask for caching, it happens inside this memory pool. If the data processing happens, it's supposed to happen inside this memory pool, Spark memory pool. Okay, so if any execution, anything, any JVM process that needs to run, it happens inside this Spark memory pool. Okay, now this user memory pool is for non-data frame operations. Okay, user memory is for non-data frame operations. That means you can consider that as a non-data frame operation means um, let's say I told you, right, non-data frame operation means like you need to store some information something. For now you can remember that user related. Okay, you are a user, you submit the application, it wants to maintain that user related information something. Let's think for that now. Okay, we will see what is this user memory pool. Okay, here are some examples. If you created what is this user memory used for? Okay, um, okay, let's see some examples. If you created user-defined data structures with such as hash maps, Spark would use this memory pool. This is a new thing for you. User-defined data structure. What is this user-defined data structure? I told you by default, the default data structure of a Spark is RDD. RDD. Okay, RDD. Anyway, all the RDD information and RDD operations are performed inside this user memory. Fine, fine. But user-defined data structures. These RDDs are by default data structures. So RDDs are default data structures. That's what we discussed, right? That's what the rule one we discussed in Spark. That's what we discussed in the first. Okay, by default structures. But this is user-defined structures. That's what that means. In future, somewhere you feel something that needs to be that's not there. You wanted to create something. You have that feasibility to create that one, and if you create that one, that needs to go and store inside this user memory. Okay. Now, Spark internal data, user-defined UDF functions are stored in this memory. Okay. So internal metadata, something. So just remember, some information will get stored inside this user memory. Okay. Um, if you see practical and all these things, then you might get better understanding on this thing. Okay. Let's not waste time on this. Okay. Um, if you're using data frame operations, they do not use the user memory. Okay, even if the data frame is internally translated and compiled into RDD. Okay, so we will use data frames, right? I told you data frames. RDD is the basic data structure, low level API. Wait, let me give you. RDD is low level API. Okay, data frame is high level API. Okay, so what is this low level API, high level API? That means the moment you write any functions or something, any logic on top of your data, if that data, the data, right, like this RDDs we can say is like plain text. Okay, if you go and it do not have any data table kind of structure, it's just a plain text. You can say for now plain text CSV file. How that CSV file looks like? CSV file looks like is let's say Ravi. Um, Hyderabad. That's it. Let's say this is the plain text. Right? This is the text. So it will simple text. But if you go to this okay, data frame, it's like a table. It's like a table. Let me show the RDD versus data frame. It's very important, but we okay. Not this image. Consistent structure. I want some image. Mm, I think yeah. Here is image. Okay, so this is how RDDs was data frames look like. See, this is the entire record. You got my right. You got my point, right? So if say Ravi, Hyderabad, Anusha, Bangalore, Karthik, Hyderabad, something. So that records comes here. But here, if you see column wise, column and row wise, see which is better for you. You need to go here and see this is record one, record two, record three, like this. But here it's kind of table kind of structure. Okay, so let me share you this as well. This is a good example. Okay, I'll share you this document. Okay, no problem, no issues. This is the document I prepared, so I will definitely share you this as well. Okay, data frame. Okay, so that's one point. Okay, this remember this. You see, right? Record and this data frame thing. Okay, so this is how this looks like. Now let's continue. Let's continue. You'll be using user memory only if you apply RDD operations correctly in your code. Okay, RDD operations. RDD operation is on the record level thing. Okay, if you want to go on the record level. Okay, and all this kind of stuff. Okay. Now, so the point is right. Spark memory pool is where all your data frames and data frame operations live. Clear, right? User memory is for RDDs, user-defined functions, user-defined transactions. What is user-defined functions? User-defined function means user-defined functions. By default, Spark will provide you. I will let you know the value. How many functions? Come on, give me some value. There's not a specific number of functions. Total count is quite large and between Spark versions. Okay. These are the functions. Okay, so it says it couldn't give the value, but they're supposed to be value. I think 254 or something. But okay, Spark SQL functions. I mean, count sum average. You see, right? Count sum average. You know that function. This concat, lower, split, rank, row number, coalesce, when. You know these words, right? These are functions. These are functions in Spark. These are functions in Spark, and these functions, you have some predefined function, that's fine. Now you have count here, that means you can go and use this count function, that's it. But what if you want another function that which is not part of this part, then you're supposed to go and create that function, right? So that function, you can, if you want to use that function, you need to make it as a user, that is user defined function, right? This is not a default function that Spark provided, that is a user defined function, right? That's what this UDF sub means. Okay, so in user memory pool, you will run RDDs, you will have UDFs, you will have user defined data structures. What is this user defined data structures? Maybe you Google it, or I will let you know in the next class. Okay, fine. Now, so the point is right. The Spark memory pool is where all your data frames and data frame operations live. Okay, you can increase it from 60% to 70% or even more if you are not using these UDFs, custom data structures, and RDD operations. Okay, that's what we discussed, right? The 60/40 thing is can be changed. The 60% can be increased and 40% can be decreased. Okay, but never go below 60%. If there is a chance also, let's not go with that, because that's where your execution level will lies, right? So let's not go with that. Okay, but you cannot make it zero or reduce it much, because you will need it for metadata and other internal things. Okay, now let's continue on the Spark executor memory pool. Spark executor memory pool. You above we saw it for 8 GB of RAM. For 8 GB of RAM, I got 4620 MB for memory pool. So till now we discussed about the user pool, but let's discuss about the memory pool. Okay, memory pool. Okay, now this memory pool is further broken down into two subpools: storage memory, executor memory. What is storage memory? What is executor memory? Let's see. The storage memory and executor memory is decided using this spark.memory.storage fraction dot configuration. One more configuration you need to remember. That's again you need to remember. There's no point. Even in data engineering in Spark, right, there are many things that you need to remember. But I'm not sure how we are going to remember. Just remember it. Okay. So storage fraction dot configuration. The default breakup value is 50% each, but you can change it using the spark.memory.storage fraction dot configuration. See, I'm again reiterating. First, there is a driver, then there will be executor. The moment you ask for 1 GB of driver memory, you will get 1 GB driver memory plus 384 MB or 10% of your memory you asked. Okay, that will be memory overhead. So if you ask for 1 GB of RAM, you'll get 1.384 GB of RAM. Okay, fine. The driver is launched successfully. Then you will come to executor. Now if you come to executor, okay, executor, the moment you ask for RAM, okay, again executor RAM will be, let's say, 8 GB. Okay, you will get 8.8 GB of RAM. Why? Because 8 GB is for your normal. You ask for 8 GB, it will give you 8 GB. This extra 0.8 GB, right, it is for memory overhead. Memory overhead in the sense like OS operations, all this kind of stuff. Okay, OS memory you can say. Okay, now 8 GB. Now again this 8 GB is divided into three parts. One part is reserved memory. One part is reserved memory, and reserved memory will be 300 MB. It's fixed. The other thing is after this 300 MB, you will left with 7700 MB. Okay. Now out of this 7700 MB, 60% will go into your Spark memory pool, and this 40% will go into user pool. Okay, user memory pool. Okay, the 60% will go into Spark executor pool and memory pool. This other thing will go into other 40% will go into user memory pool. Okay, see, 60%, 40%. This is where you got let's say 8 GB of RAM will be divided into below three parts. Fine, you got three parts here. Now you discuss this thing. So what happens here? What happens here? Till now we discussed, but now we are zooming into here. This 60%. This 60%. We're zooming into the 60%. Okay. Now let's zoom into that 60%. What happens inside that 60%? Let's come here. This is how this RDD was data frame. This is a good example. I hope you understand this. Okay. So this we always go with this data frame only, prefer data frame only. But we'll see how we can discuss on this coming classes. Okay. So where are we now? Okay, the default breakup value is 50%, but you can change it using the spark.memory of action.configuration. Okay, so remember that. Okay, so Spark will reserve 50% memory for each storage and executor. Okay, just remember that storage and executor. I told you, right? The in Spark you are going to cache it, you are going to process it. Okay, you cache it. Where do you cache it? Where do you cache it? Okay, so for caching, right, the Spark, right, I think I meant to draw this picture. Wait, let me show the image. There's supposed to be some image here. Yeah, this is the image. Okay, so this is image. So this right, this Spark memory pool, right, 60%, right, this 60% is divided into like this: executor memory, storage memory. Okay, executor memory, storage memory. Let's see how this 4620 MB is divided into execution memory and storage memory. This is like we call as unified memory. Like for now 50%. Okay, if you want to change, you can change it, and it's automatically changeable as well. Let's see all these things. But you remember this. So always remember, we are inside this 60%. We are inside this 60%. Okay, inside this 60% Spark memory pool. So we are discussing all these things here. See, storage memory pool, executor memory pool. That's what we are discussing. Okay, currently. I hope this will be very new, so much overwhelming content. I'm sure, pretty sure. But after this class, in future, at some point of time, you wanted to refer this document again, learn these concepts again. Then this document and this class will definitely help you. Okay, so that's why I'm a bit deep diving. Okay, just 20 more minutes, we will be done. Okay, just 20 minutes. Okay, now executor memory, storage memory. Okay, executor memory, storage. Let's see. 50%, you know how it will be done. So Spark will reserve 50% of the memory pool for the storage pool, and remaining 50% comes to the executor pool. Perfect. That means 2310 MB into storage and 2310 into executor. That's it. Storage pool. What happens inside the storage pool? What happens inside the executor pool? Very simple. Storage pool means you want to store the cache the result, cache the some data. Okay, that caching will happen inside this, and this 2310, right, this is where your processing will happen. You need to prove some processing rate on top of that data. That processing will happen here. That storage and execution, you can say. Okay. From the joining and the buffer is created in the from the joins, that buffer is created in the executables. Here it says joins because when I practiced, when I learned this concept, I use this join concept. But you can think of like you load the data and that intermediate data, right? Intermediate data, some intermediate output you need to save somewhere. That you can save inside this storage pool. Okay. Now, um, similarly, if you are aggregating or performing some calculation, the required buffer comes from the executor pool. How we can say is this aggregation functions and all means count, sum, average, all these are aggregated functions. That means sum means you will calculate all the rows and on top of that you will get the sum. Count means count all the rows. Sum means all sums, all row sum. Average means on all top of all rows you will do some average on all this kind of stuff. Okay. Now, so executor pool is short-lived. Okay, you will use it for execution and free it immediately as soon as your execution is completed. So that's what we discussed it. Executor memory is short-lived. Executor memory is short-lived. The moment you load the data, you process the data, that's it. So it got processed and that executor memory is released the moment it got processed. But storage memory is not like that. Okay, it is used for caching your data frames. So if you are using data frame cache operation, you will be caching the data inside the storage pool. Okay, so the storage pool is long term. You will cache the data frame and keep it there as long as the executor is running for you. Okay, and or you want to uncache it, uncache it. As long as that machine is running, okay, you store it inside the storage memory pool. Okay, the data will lies there. Okay, the moment this executor got switched off or something, you until this you switch off that executor or something, it will still there, or you will uncache it, right? I told you that uncaching as well. The moment you cache it, it's always good practice to uncache it as well. Okay. So just remember this again: 50%, 50% to memory pool, 50% to storage. Okay, 50% for execution, 50% for storage. Okay. Now out of this 4620 MB storage and 2310, I will go into storage. 2310 will go into executor. Okay. So this is joins and executions aggregations. So what happens is this is the concept like how joins will happen is right, the data needs to travel whenever join, right? If you perform join means wire transformations, the data needs to join. Okay, data needs to join, and while how the joins will happen is, let's say right, that word count program, famous word count program, right? So this same related information for each key supposed to go and sit into same container, same executor or something, right? That's what we discussed, right? Same keys supposed to go and sit inside the same place. Then only that the joins and all will happen correctly, right? So that buffering and all, everything will happen in the executor. Also this aggregated functions. Aggregated function means I need to calculate aggregations. Let's say there are 10 partitions and 10 executors working on top of that. I want the sum of that. And how it will happen? This entire sum of the one partition will be done, and that value is stored in the same partition, in the same executor. Again, for all these 10, right, there will be 10 values now. All these 10 values, I need to sum it again, right? So all these things will happen inside the executor only. Okay, inside the executor only. If you're aggregating or performing some calculation, the required buffer memory comes from the executor port. Buffer memory. So where these partitions are loaded into executor memory only. So once it's loaded, the calculations happen and everything is calculated inside that executor memory only. So you're not storing it, you're just calculating it. Everything will happen inside that executor memory only. So the joins means, if you remember that a join concept where select star from employee table, inner join, the department's name on employees dot the department ID is equal to departs dot department ID. So some joining needs to happen. That's a different data. This is a different data. Employments and departments. The data needs to join now. That means data needs to shuffle. Okay, and shuffle and data related to each key is supposed to sit in one place. Then they can do the join on top of that. Okay, but you will understand more when you learn these join concepts. Okay, now where are we? Okay, the storage pool is used for data memory caches. You know that. Okay, so if you are using data memory data frame cache operation, you will be caching the data in the storage pool. Okay, that's what we discussed. Right, storage pool is used for storing the cache data. So if the storage pool is long term, you will cache the data from keeps it as long as the executor is running, or you want to uncache it. Fine, till here fine. Now let's take a look at angle of CPU cores. CPU cores. Okay. CP cores. I told you about, right? Yesterday also we discussed executor cores, CP cores, whatever you call CP cores. Okay, let's know. If I ask for the four CP cores, then my executor will have four slots, also known as thread, or and we can run four parallel tasks inside these slots. That's what we discussed, right? Four CPU cores means four parallel tasks you can run. Now, as these slots are threads within the same JVM, we do not have multiple processes or JVMs here. All we have is single JVM, and all slots are simply threads in the same JVM. Okay, so it says that we have four CP cores. That means you're not going to have four separate JVMs. It will be same JVM and these four slots inside that. Okay, so that means four slots inside means four tasks can run parallelly inside that JVM. Okay, so if I have one executor JVM, 2310 memory will be go to storage pool, and another 2310 will go into executor pool, and four threads to share these two memory pools. That means now you decide this 231 MB, let's say four CP cores, right? We asked for four CP cores. Let's say four CP cores means out of this four, if I divide 2310 by 4, that means it will be 500 75 77.5 570.5 MB will go to one executor. I mean one slot. Okay, 575.5 MB will go into one slot. We have four CPU cores here. That means each CPU core will get 575.5 MB. Okay, where it got it from? Via this executor memory. Okay, so how much executor memory will get each task means it will get 2310 by 4, right? That's what it says. Okay, the static memory management and Spark used to assign task memory using the static method before 1.6, but now they changed it and implemented a unified memory manager. See, till 1.6, Spark 1.6, this is what this static memory management. That means this 50-50 thing. Okay, but after this, they changed it. How they changed it? Unified memory manager tried to implement fair allocation among the active tasks. Let's assume if you have two active tasks, and actually there are four slots, but I have only two active tasks. So that means how much memory you will get now? See, again, let's say inside JVM you have four slots. Fine. The total memory of that JVM is 2310 is storage pool, 2310 is executor pool. That means you will get 575.5, let's say 500 for now. Just go with 500. That's it. Okay. Let's keep it simple. 500 MB for each slot. Okay. That means you have four slots. Four slots. Okay. Now, out of these four slots, you have only two tasks running inside that. Two tasks running inside that. That means you will have 500 MB in till 1.6 Spark 1.6 till Spark developed, right? Version means till maybe in 2020 2022 something till 2022. This task, right? This task will have 500 MB for each task, 500 MB, and the other two is idle. No one is using that, just sitting like that, just sitting doing nothing. That's it. But for after 1.6, it changed. It got changed. Okay, because if you're not utilizing that extra 500 MB plus 500 MB two slots, why waste that memory? Why can't these two active tasks can use that? Okay, why can't they use that, right? That's what they discussed, right? Let's assume if you have two active tasks and actually have four slots, but I have only two active tasks. So the unified memory manager can allocate all the available execution memory amongst the two active tasks. Okay? You can think in this way as well. So even though you have four slots, four tasks can come and get executed there. But here what happens is there are only two tasks running, only two slots are filled and the other two slots are empty. Okay, you can just utilize those two tasks those two slots as well. I mean those two slots memory as well. See, in theater, let's say in theater capacity is 300 people. Okay, only 10 people went into the theater. Can these 10 people go and sit anywhere, right? Anywhere, and they can utilize entire theater, right? So see, you can think in that way. Okay, so you can just go there, and if no one is there, then you can definitely go and utilize that. Okay, simple. Now the point is straight. There is nothing reserved for any task, no individual task. Okay, nothing is reserved for any individual task. The task will demand the execution memory, and the unified memory manager will allocate it from the pool. Okay, so he is a memory manager here, so it will allocate the memory for that. Okay, if the executor memory pool is fully consumed, then memory manager will allocate some memory from storage memory pool as long as we have some free space. See, This storage memory, the executor memory, they got 500 MB. Okay, for now, let's say there are four tasks running. Four tasks each got 500 MB of executor memory pool and 500 MB of storage memory pool. When they're running, if they want more than this 500 MB, okay, they Spark, this unified memory manager will give, let's say they want 100 MB more, then that 100 MB they will get it from the storage memory pool and give it to the executor memory pool. Okay, so see, simple. I told you right here, executor memory, storage memory. The task is running. Let's assume with only single task. One single task is running here. Okay, the running will happen here. Caching and all will happen here. This arrow, right? It can move here, further here and there. Okay, so I can move this arrow here. Okay, and till here. That means, let's say this is 1 GB of data. Uh, I mean 1 GB of data. This is 1 GB. 1 GB of data is divided into two parts. 500 MB, 500 MB. This 500 MB, right? If I move it here, this will execution will get only 400 MB. This will get 600 MB. If I move it further, it will get 300 MB. It will get 700 MB. If you move it further, it will get 200. It will get 800. Like that. This array is movable because in real time, if a task needs extra memory, it will get from the storage memory pool if it's free and give it to this task to get it completed. Okay, as we know that we started with 50-50 boundary between executor memory and storage memory, we can also change it using spark.memory.storage section. See, we can change that. That's what we discussed. This 40-50-50 can be changed. If you do not cache too many data frames, then we shift this flexible boundary to 30% as required, and borrow space as long as free space is available. I told you, right? So this 50-50, we are going 50-50. Executor will get 50%, storage will get 50%, but you can change it. You can change it to 70-30. Okay, let's change it to 70-30. Okay. Similarly, each memory manager can also borrow some memory from the other side of as other side as long as other side is free. That means, let's say you're not doing much processing, much processing, but you're not doing much processing, but the storage memory you wanted to cache some big amount of data. Then while caching it, right, that memory is not enough. Then you can just borrow from this executor memory as well, execution memory as well. Okay, let's assume we cache some data frames, and that caching entirely consumes the storage memory pool. But I want to cache some more data, so the memory manager will give me more data memory from the executor memory pool. Okay, that's why we told, if you cache, let's say you have 2 GB RAM and available for you for execution and caching and all, total, if you're going to use this 2.5 GB of data to cache in the here, that means it will utilize entire memory, and you will reach the out of memory issue, execute out of memory issue. Okay, so remember, boundary is a grid. If we reach the boundary limit and executor needs more memory, then memory manager cannot evict any changed data blocks. Okay, so first let's see here. We borrowed it from the executor pool. Okay, where we are. The executor will start consuming memory as long as there is a free space. Okay, but in the end, the memory manager will evict the cached data frames and spill them to the disk to make more space available to the cluster. In future, if some new task I need to get in and I need to process that, then what happens? We have a boundary limit, right? Boundary limit. So till 30%, the caching will happen. Okay, till let's say 50-50. For now, 50-50 only. Till 50% caching will happen. Okay, let's say you get in some data into here, that will be cached there till 50%. If you want extra 10% or extra 20%, it will give you that extra 10-20%. But what happens is, if any object comes for processing, it will remove these 20%. It will remove this 20% and spill it to disk. Okay, see, remember, um if there is let's say you booked a seat in theater. Okay, so but there is a recliner as well in the theater, but you booked the normal seat. Okay, you enter the theater and you sit in your place. Okay, but after 20 minutes you realize that there is no one in the recliner. You can go and sit there, but sit there as long as the person who booked that recliner comes in, right? Who wants to utilize that recliner comes in, right? Similarly, in the Spark, right, the execution and storage pool. So if your storage pool wants some memory, executor pool will give it. Okay, if executor wants some memory, executor pool, then it will get some memory from the storage pool. Okay, they both can help each other until they are busy with their own task. That means storage memory needs some extra 20%, the executor memory will give it. But here what happens is, if any data came for processing, then this storage memory will evict this 20% and put it into the hard disk. Okay, similarly, this executor memory, right? Executor memory might utilize this storage memory as well for execution and all, but in future if something is cached, that means it will spill that extra executor task, right? Extra executor memory, right? That it will remove and use that space for caching the data. Okay, that's what it happens in the background. Okay, we borrowed it from the executor pool, and now the executor needs it back. See, I borrowed from the executor pool, and now the executor needs it back, so the memory manager will evict it and give it back to the executor pool. See, that's what we discussed. If it needs it again, it will give it will get it again. Okay, so remember, boundary is rigid. Okay, if we reach boundary limit and executor needs more memory than memory manager cannot evict any changed data blocks. Okay, boundaries rigid. If we reached boundary limit, an executor needs more memory than memory manager cannot evict any changed data blocks. Okay, if it was free, the memory manager should have given it to the executor. Okay, if it's free, it's available, free space available, then it might have given it. If it's not available, it cannot evict any change data blocks. Okay, it cannot evict means it cannot remove any or change any data blocks, which is already part of that. Okay, if it's free, it might have given. If it's not free, it cannot give it. So simple. However, the executor needs more memory. So what happens? The executor will try to spill few things to the disk and make some more room for itself. The feature I told you, right? It wanted to import, let's say, 2 GB memory is the executor memory. It will try to import only 2 GB. The moment it processed, that intermediate result will be spilled into the data disk. We discussed this concept when we discussed about what if my cluster size is very less compared to the data I need to process. Okay. Now the executor needs more memory. So what happens? The executor will try to spill few things to the disk. Okay, and make more some more room for itself. Okay, what if you have scenario that where you cannot spill to disk? Okay, that means super, you hit the out of memory exception. Your job will fail. Okay, what if you have a scenario where you cannot spill to disk, the disk is also full, but you had to process many things? That means you will hit a memory issue. Okay, you need too much burden for Spark. That's why you will reach this, you will hit this out of memory exception. Note, Spark memory management is too complex, but you should understand the structure so you can manage things more efficiently, and you can follow the configurations to control it. Okay, so always remember this thing. Okay, the Spark executor memory overhead will give you 10% extra of whatever you are asking for the JVM, and is outside the JVM and reserved for overhead. The moment you ask for 1 GB, it will giving you 1.384 MB, or if you ask for 8 GB, it will give you 8.8 GB. Right? That extra is used for outside the JVM and reserved for memory overhead. Memory overhead means OS memory, OS related things. Let's say your JVM memory comes with Spark executor memory, and this configuration allows you to ask for the executor JVM memory. Okay, executor JVM memory. Okay, and whenever you get, the Spark engine will receive 300 MB from your allocation. No, right? 300 memory for allocation, reserved memory, and extra 60 40%. Now you configure the Spark memory configuration to tell how much you want to use for data frame operations. The default value is 60%, but you can increase it. The leftover is kept aside for non-data frame operations. Here it is user memory, 40%. Uh, 40%. By default, 40%. Okay, 40%. The Spark memory storage function allows you to set the hard boundary, then the memory manager cannot evict. Okay, it cannot. If I say 60/40, 60/40, that's it. It's 60/40 only. Maybe if the space is available, it can be used, but by default it's 60/40 only. That's it. If you're not dependent on the cache data, you can reduce its hard limit. Okay, hard limit. Okay, finally, executor cores. Ideal range is 2 to 5 executor cores. Okay, 2 to 5 executor. That's what it's. The optimal value is 5. That's what we discussed yesterday. Max, but that doesn't mean you can go to one as well. Okay, no, never go with one. It's very waste of efforts and all. Okay, always it's better to go with 2 to 5 executor cores. Course. Okay, I prefer just go with three. Mostly, most of the times go with three. But if the big data, you need to process so much amount of data and all this kind of stuff, let's say and 1 TB of data you need to process, then it's good to go with the five executor cores. Okay, executor core is critical because this configuration defines the maximum concurrent threads it has. It says parallel maximum parallel tasks. Okay, that's what we discussed, right? Let's say there are 8192 partitions and you have only 100 executor cores and only 100 8192 out of 8192 partitions you can process only 100 partitions at the same time. That's it. The next you need to get it into the next batch. Okay. If you have too many threads, you have too many tasks competing for the memory. If you have a single thread, you might not be able to use the memory efficiently. See, this is the issue. Someone asks you that you have only one thread, one executor core, you cannot use the memory efficiently. One executor core is using the entire memory. That's it, simple. But if you have too much amount of executor cores, that means you are going to, let's say you have some 10 cores and you have 1 GB of data. That means each will get 100 MB. 100 MB means it's very less MB because you have 128 MB of partition. You cannot input that 128 MB of partition, right? It will fail. That's what, you cannot have the more number of executions, you cannot have the less number of executor cores. Okay, so that's why I always go with some optimal value, 2 to 5. Okay, so more than 5 cores can cause excessive. In general, Spark recommends that 2 or more cores per executor, but you should not go beyond 5 cores. Okay, more than 5 cores can cause excessive memory management overhead and contention, so they recommend stopping at 5 cores. Okay, some memory controllables. Let's see some memory controllables. I'm pretty sure it will be understandable for you. Let's see. Executor memory overhead. Gamma spark. Yeah. Someone want to say something? Okay. So Spark memory overhead, Spark executor memory. Okay. Mm, okay. Spark memory fraction, Spark storage memory fraction. Remember these things. Okay. This will help you to control your heap memory. Okay. And these things will help you to control your off heap memory. Off heap memory. Okay. These things. This is for heap memory. Heap memory is nothing but your execution. Execution will happen in the heap memory. Mm, then where is this? Okay, so this helps to control the on heap memory. These are the memory controllables. You can just remember. I told you already. These are the formulas. You can just remember these formulas. So maybe you can take this as a task. Take these memory configurations, and we can talk. You can write. I'll share this document with you. So you can write the its description here. What does this memory overhead do? What does this memory do? What is this memory fraction? What is this storage fraction? What is this executor course? Executor course you already know, but just write the description on your own words so that you can complete this document. Okay, um, that's it. I think that's it. Now let's see these three. Just a small thing. Let's complete these things. I got write some notes as well. So these three: Spark memory, right? Off heap memory. These three: Spark dot memory, off heap enabled memory, off heap size, executor PySpark memory will give you off heap memory outside your JVM. Okay. We already know that most of the Spark operations and data caching are performed in the JVM heap. We know that. I told you right, JVM and non-JVM. JVM means execution. That's it. Non-JVM means non-execution. That's it. Non-execution tasks. There are many in your system, right? There will be many things, but you never worry about all those things. Everything will be taken care by your system itself. You never worry about these things. Okay. So, however, JVM heap is subject to garbage collection. If you are allocating huge amount of heap memory to executor, you might face excessive garbage collection delays. So, garbage collection. So, out of you three, does anyone have knowledge on garbage collection? Anyone? No idea on garbage collection?
No, sir.
Okay. You guys work with Java or C? Anyone? Any idea on Java?
Yeah, yeah,
Nothing.
yes, sir.
Yes, sir.
Okay. So do one thing. Do one thing. Go and search for Java garbage collection. That's it. What happens is Let me give you a small quick example. I'll tell you. Okay. I wrote a code. Okay. Code df is equal to, sorry, not df. Let's go with list. List one is equal to some big number. Some big number. Okay. Sorry, list 1 comma 2 comma 3 comma 4 comma 6 comma something, some number. Okay. But I never use this list one in my code. I never use this list one in my code. Okay. I created this list one, but I never use this object. List one is an object in Python. List one I never used. So does I need this list one if I'm not going to use it? Yes or no?
No.
No. Then these things, right? This object is unreferenced, right? This is unreferenced. In let's say if I can write this as well in Spark. Okay, so I can write this as well. So I mean, write this code as well. But if it's not used anywhere, that means it's not helpful, right? So these things, there are some garbage which are not needed for the to run the program. Okay, there are some objects which are unreferenced objects. I can say these unreferenced objects are not needed. Those things can be removed. Those can moved into garbage. Okay, so that's what garbage collection means. But it's a big
It
concept.
is like
Hmm.
uh, like
Unnecessary.
before we have used it, but no longer needed or something, right?
Not no longer needed. I mean, you never used it.
Okay, we never used it. Okay.
We never used it. You created it, but you never used it.
Okay.
It's unnecessary, right? If you are not going to use it, then let's not create it. But
Okay.
we are a bad program. We created it. Then this garbage collection will take care of that. But just Google it. What is garbage collection? That's it. Okay. What is garbage collection? What is garbage collection delays? Those two things. And what is off heap memory, on heap memory? That's it. These three, four things are just try to Google it. You will understand better. Okay. If I explain that as well, it will be very lengthy and you will feel exhausted. Okay, so I know you already started feeling exhausted, but yeah, let's go there and search for that. Okay, mm, that's it.
Yes, sir.
Just one more thing, you know that Spark is JVM application because it was written in Scala. PySpark application might needs a Python worker for extra libraries. Okay, so Python workers uses off-heap memory overhead. Python workers use off-heap memory overhead only, and to set that off-heap overhead memory of for Python workers, you can use Spark executor dot spark dot memory. Spark does not set it. I think you understand the cluster. I think fine, but this is bit okay. No problem. I'll share this with you, but in the coming class, I will explain you this. Maybe with example. Now, if I say, you won't get anything into your mind. I'm pretty sure. Okay. So in the real time,
Yes.
some extra, like, what happens is, maybe remember this point in future. Maybe um, what happens is, Spark is your cluster is created, driver is spin up, executor is spin up. What are the applications that are running inside that driver and executor? What are the applications that are running inside that? In my system, there is Chrome, there is File Explorer, there is Outlook, there is Teams, there is Chrome, there is Firefox again. But these are the applications that are running inside my machine. But in Spark, right? It's not apps. It's not apps. I'm telling. It's just application. Okay, just application. So what are the things that are running inside? Maybe in my system, I know that this is running inside me. But in Spark, right? Executor and driver, what should be running in? They do not need all these applications. Do they need all this Chrome and all? Are you going to go and use it? No, not going to. They need is what they need is Java. If you want to run Java, you need to set up the Java environment. If you want to run Spark application, you need to set up Spark environment, right? All these things, simple, right? So this is my laptop. That's why I need all these things. But if you are using just RAM and ROM CPU from the remote means in real time, right? You will never going to see where these jobs are going and running in, where this data is being executed. That's it. You'll never going to see. So that's why you all you need is just setup. Setup means Spark related to environment. That's it. Your data can go and get executed. That's it. So that's why Spark will do some internal things so that to launch those libraries installed and all. So I will show you those things when I'm discussing on the EMR part. Then you can understand more on these things. Okay. For now, that's it. So just we covered 90%. I think there are advanced concepts here, but I'm not touching those concepts. Otherwise, it will confuse you, and in interviews also, right? You won't get any questions on top of that. Why just stressed unnecessarily? So this is what I prepared when giving my last interview. So that's why I showed you this. But in the document, it's a bit different. Okay, bit different and all. But if you are okay, just you go with these concepts. Okay, here memory management in Spark, driver executor. Again, see this Spark memory management. There are two things here: executor memory management, driver memory management. Driver we know. Uh, Driver we know. Driver is driver plus driver memory overhead. That's it. If you ask for 1 GB, it will give you 1.384 MB. That's why nothing is interesting here. There is nothing. Driver is very boring. Okay. But if you go to executor memory, you have two parts here: off heap memory, on heap memory. If you go here, this is the node manager. Okay. This is the executor container. Inside the executor container, you have heap memory, off heap memory, this overhead memory as well. Okay. Now in this heap memory, you have two more things. You have literally three more things: executor memory, storage memory, executor memory pool, azure memory pool, user memory pool, 60%, 40%, and 300 MB. Okay. Now off heap or heap. Then if you go here again, you can understand this off heap, on heap, everything. So this is movable. This is movable. Okay. It can come here, it can come here, like this arrow, right? This arrow is movable, dynamic occupancy mechanism. Okay. So all these things. So you can go through this as well document. This is also understandable well, but if not, then I will share this document as well, then you can refer this document as well about anything. But this is what I prepared with my plain words. If you see, there are many grammar mistakes here. I'm still correcting while on the call, right? So that's why. So this is what I prepared using while my interview. So it will definitely help you. Okay, I'll share this as well. But the most majority of the concept, right, which any concept which is not understandable, I'm not understandable means I haven't covered in this here. Okay, so which is not important. Okay, so these things, right? This last concept is not important, because just till here it's important. After this, not important, because I gave at least 50 plus interviews, but never faced this question. And I never asked. Whenever I take interviews, right, I ask any question, then no one will answer this question, because this is that advanced and very less used in the real time. So no problem. So till here, okay, till here.
Sir, can you send it in WhatsApp, sir?
Yeah, sure. Till here, if you are able to grab it, you'll be good. Okay, till here. I'll send this in the
Yes, sir.
okay. I'll send in the document. Okay, just uh, learn this concept, because the garbage collection and all. Why I'm not covering is, it's supposed to be done in Python. You guys supposed to have Python knowledge. Python means you're supposed to have this knowledge as well. Garbage collection. At least you know Java. In Java, you might have had this garbage collection. At least you might have familiar with that word. But that's okay. You can just Google it and learn it. Okay. That's it. We are done with the Spark memory management as well. Now we are left with Spark submit. Okay, Spark submit, and this data frame dataset we will see data skewness, Spark submit, and what else? Broadcast and accumulators is nothing but, yeah, handling failures and all. Okay, that's it. So we left with three more concepts. Maybe we'll be done in by Tuesday. Tuesday we won't have class. Okay, 99% we won't have class on Tuesday. Mostly we will continue. Monday we will have class. Okay, tomorrow we will have class. Tuesday we won't have class. Wednesday we will have the class. Okay. Um, So hardly two more concepts, 2 more days, two more sessions. Maybe by Wednesday you will be done with this Spark, entire Spark. Okay. I'm expecting a demo from you on Saturday or Sunday. Is that fine? It's up to you. So if you have any project works or something, so just let us know earlier only. It's up to you. But yeah, mostly by Wednesday you'll be done with Spark. Okay. And I'm planning to start this what we call practical as well, just small practical. Okay, because if I start practical, you won't understand anything. Why? Because you have to go through these concepts first thing, and next you are not familiar with this Spark coding, not even Python. I think you guys know Python. You're supposed to learn, right, on Python on your own. Veda and Anusha,
Yes, sir.
you know Python, how Python works.
Yes, sir.
Python coding and all. You start practicing, right? Whether you also started practicing, right?
I have started practicing, but I've stopped now because
Hmm.
Spark is going on now. So that's why I was
Yeah, but
seeing the
but
theory.
we discussed, right? Every day you're supposed to work on SQL and Python problem, at least one problem in a day.
Yes, sir.
Okay, it's up to you. It's up to you. So just try to practice this Python and SQL. But from my side, I'll try to arrange at least two classes on Thursday and Friday to show some practical things. Okay, some practical things. That's it. So I will show you. Maybe you understand or do not understand. It's okay, fine. Just see how things happen in the real time. That's it. Then then if you see, you will have some idea in future. If you wanted to practice it, if you wanted to see, you will have something in your mind, okay, to work with. Okay, that's it. From Monday onwards, I mean next Monday, not tomorrow. From next Monday onwards, you will start with AWS. Okay, AWS S3, Glue, Lambda, all this kind of stuff. Okay, then within 1 week we'll be Redshift and all. So within 1 month, sorry, one week we will cover entirely on AWS, and after that next week we will practice. We will do some projects. Okay, um, I think wait, let me. So from 20 to 25, sorry, 24, we will do some learning on AWS tools. Okay, if you guys okay, let's have a class on 25 and 26 as well, same times, or whatever works for you, class, and then do some project as well on this AWS learnings. Okay. Then from 27 to 30, 31, let's have some demo on this Azure as well. Then have let's one project on this 1 and 2. That's it, October 1 and 2. So you have two tools, cloud tools, and two projects as well. Now, this project one you will done on top of AWS. Prior to you will do on top of Azure. Okay. Now, in the next this week, right? 3 to 8 or something. I'm not sure till how long this course is for, but yeah, if you guys okay, then within this week we can connect for the doubt session, all this kind of stuff, and we can perform this. That the project we done on top of AWS, we will try to replicate it in the Azure. The project which we done on top of Azure, we will try to replicate in the AWS. That's it. In that way, you cover two projects, two tools, Azure and AWS. Okay, so you have Spark covered, Hadoop covered, these tools covered. But Python and SQL is up to you. So you guys need to practice. I'm not going to involve there, but I will give you the resources and all. Okay, I mean you already have the resources. In fact, okay. So just utilize those resources and start practicing. That's it. Okay. Maybe within 2 3 weeks you will be done with these things, but I'm not sure when they are going to schedule last day and all. I'm not sure, but yeah, within maybe October first week also we will be wrapping up with these things. Okay, so that's it for today's class. Any doubts? Anything? I know you will be exhausted and all. These are new concept. Okay, even though I know this concept, if I go through this concept again and again, there will be many things I will forget. But that happens. There are many things that you need to. At least you should. If you are aware of these things, right, it will be good. Okay? And pretty sure in interview you are going to get some memory related questions. Okay, maybe problem we discussed yesterday, how executor cost, executor size, and everything will get decided. That one kind of problem, or this memory, how memory allocation happens in Spark. That's one kind of problem. Okay, just be thorough with these concepts. Okay, simple, simple. Okay, so always go and say Spark interview questions. For fresher, let's say your freshers, right? Everyone is fresher. To give you the number of questions. Okay, give you see this guy is very good, guys, with metal. He will give you some questions. What is Apache Spark? Spark better than MapReduce? Why? Key components of Spark ecosystem: RDD, lazy evolution, shuffling, coalescing. Purpose of coalescing: what are data frames? Distributed collection of data organized into named columns, similar to table in a relational database. That's what we discussed today, right? It's kind of table structure. Okay. There are more optimized than RDDs due to schema information and catalyst optimization. Okay. So what are the Spark supported file systems? Okay, then the file system or HDFS S3 local file system. Spark streaming not needed. Okay, we are not doing Spark streaming. What is caching? Right, ability to persist data in memory across operations. Okay, this is how you will get questions. Top 80 Apache Spark questions. Simply learn, right? Go here and see what are the questions here, and see you will have most of the concepts covered here. So just try to prepare on top of those things. Okay, I'm again repeating: one SQL a day, one Python a day, okay, and one concept a day. Any concept, whether it's a Spark concept, okay, Spark concept, or in AWS tools, something, any concept. But if you try to follow these three things, then you'll be good. Okay, so that's it. Okay, I'll share you this document as well. I'll share you this document as well. Yeah, that's it. That's it for today class. If no doubts, we can wind up. Okay.
Yes, sir. Thank you, sir.
Thank you. Thank you so much. Bye.
Bye, sir.
Bye, Karthik. I know you are unable to speak, but yeah, thank you. Thanks for the class.